All right, so here's number 12 from the assignment. That's where we're starting. An interstate driver is traveling 420 miles across the state from south to north without stopping. At noon, she notices her speed is 60 miles per hour, and her position is at mile marker 240, and it says interstate mile markers increase from south to north. Use this data to write a linear function, which could be used to estimate her position as a function of time, and assume t equals 0. So if I need a linear function, normally these are the letters we use. In this case, instead of x, we're going to use t, and instead of y, we're going to use the distance. And the slope is going to represent the speed that she's going. That's the rate. So in the question, it says that she's going 60 miles per hour. Use 0 for t. That means if she's starting at the 240 mile marker, that means at 0, her position is 240. So we're going to use those values to write a linear function. So I'm going to use these letters instead of x and y. It's going to be okay. So instead of y equals, d equals the slope, t subtract 0, it's just t, and then add the y coordinate, which is d, which is 240. So if I put this together, that's 60t plus 240. In A, that was A, right? In B, it says approximate her position at 2 p.m. So at 0, it's noon, so 2 p.m. would be 2 hours later. So I plug in 2 for t. And the approximate would be 120 and 240. I can do that. 360 mile marker. And then C, approximate position at 10:30 a.m. Well, that's going backwards in time. So with this, we can go backwards in time. So the number I'd put in for t then would be back an hour and a half. So noon is 0. To get to 10:30, you go back 1.5 hours. And then what was the mile marker going backwards? So what's that? Dear me. Negative 60, half of 630. Is that negative 90 plus 240? So that would be 150 would be the mile marker. And then D says, what's the domain of what's happening here? So the first domain, in terms of what can be applied, in terms of hours. So if I look here, if I made this equal to 0, that would be one domain restriction. So if I made that equal to 0, that'd be minus 240 divide by 60, that would be minus 4. So at minus 4, that would be at 8 a.m., the mile marker would be 0. And then how about the other direction? It's 420 miles. So I'm going to make it equal to 420 miles. Subtract 240. 180. Divide by 60. So that's the end of the trip, and that's the beginning of the trip. In time, that would be from 8 a.m. to 3 p.m. And we're saying t equals 0 equals noon. You know what? It's not a particularly difficult one, but it's an interesting one, so I like that. Number 13. All right. Here are some review questions. In number 13, it says, use the graph of the derivative to sketch a graph of both the second derivative and the function with a starting point. So let's look here. What am I looking for to begin with? Where are the x-intercepts? Let's do that. I'm going to do 13 and 14 together. So the x-intercepts are at 0, at 3, and really 5 is the end. So 1, there's an end point at 1. and the other one has an arrow. So really we're looking at 0 and 3. It's below and then above and then above. So below, above, and above. If I was looking at the second derivative, where are the turning points? So we have a turning point at 1. We have another one at 3 and another one at 5, or 4 I mean. And it increases and then decreases, it increases and then decreases. Now 4, the slope is undefined. Because the derivative is undefined at a corner, that's going to create a hole in my graph at 4. Alright, so let's just break this down to begin with. So it's increasing, and then there's a turning point. Now, for my second derivative, that's like the point of inflection at 2. So when I draw the second derivative, what are the things I'm looking for? So these numbers, 1 and 3, 4 and 5. These are x-intercepts. And at 4 is a hole. All right. At 2 is going to be a turning point. So this starts above and then goes below. So it goes above, then it goes below. It turns at 2 because that's the point of inflection for the derivative. And we're going to go all the way to 4. Now at 4 is going to be a hole. And now from 4 to 5 is a slanted line. So the derivative of that is -3. So what's the slope of that line segment? The slope of that line segment is -3. So this is the slope from 4 to 5. This represents the slopes from 0 to 4 and the hole there. That turning point comes from the point of inflection. The x-intercepts, right, are the turning points of the derivative. So it is increasing and then decreasing, then increasing again. I know it's a little challenging. How about the function itself? From 0 to 5. What things am I looking at there? It says there's a starting point at 0, 0. So I'll start there. If I look at 0, 0 here, 0 is a minimum, and that's it. Everything else rises from there. So it's concave up. So it's concave up to 1. And then after 1 it increases completely, but now it's concave down to 3. And then to 4, it's concave up. And then it just keeps going concave up after that. From 3 to 4, it's concave up. And then after that, it's concave down as it rises. Oh, and it ends at 5. So right there is an endpoint. So if I follow, it decreases and then it increases after 0 all the way through. It's concave up, concave down, concave up, and then concave down. Putting it together. Number 14. That was 14 and 13. Number 15. At number 15, find the absolute extreme. So I have a function. To find the absolute maximum or minimum, I need to do a table of values. In that table of values will be my ends of my interval, which is -1 and 3, and also any critical numbers that are in that interval. So to find the critical numbers, take the derivative equal to 0 and solve it. So I get 1.5 or 3 over 2. So that is in my interval. And then to each one of these, you plug into the function. So if I plug in -1, I get the answer -4. If I plug 3 in, I get the answer 0. And if I plug 1.5 in, or 3 over 2, I get 9 over 4. And then if I want to know what the absolute max is, what's the biggest number in that group? That's 9 over 4. If I want to know the absolute minimum, what's the smallest number here? And it's negative 4. So that's my maximum minimum. Good review, right? And if a question comes up like that, those are one of the easier questions. Number 16. The second of two positive numbers is the reciprocal of the first. So I have two numbers, and the second number is the reciprocal of the first. Find the two numbers so that their sum is a minimum. So I have the first number, and the second number is the reciprocal of the first, and I need that to be a minimum. So I already have an equation with one variable. I'm going to make it friendly and then take the derivative, and then I'm going to solve it. So I make sure I make it equal to 0. I'm going to add 1 over x squared. I can already tell the answer is positive and negative 1 because it's positive. The numbers are positive, so it's just positive 1. You can tell if you plug 1 in, it satisfies the equation. Use your gut. Or you can keep solving it, multiply by x squared and square root. And then is that a minimum? And so into the derivative, if I plug in 1/2, when you do the reciprocal, you get a negative. If you plug in 2, you get a fraction, so it's smaller than 1. That's a positive. So that is a minimum. So the question is, find the two numbers. So one of the numbers is 1, and the other number is the reciprocal of that, which is also 1. So both numbers are 1. Like a white frog looking at you. All right, number 17. Do you see the frog? I see things. All right. We're given a function, 4,000, 1 plus 100, e to the negative 0.5x. This is a logistic growth question. So it grows and then flattens out. And then it says you might use a calculator. Ooh, I have one of those. It says how many people have become sick by the 10th day. So for the 10th day, I'm just going to plug in 10 into the function. Use your calculator. Here, let me show you how I would use my calculator. And because I'm doing a lot of things with this one function, I think I'm going to define it. So I'm going to pretend like I'm going to graph it. Press tab. I'm going to go back 1. I'm going to erase whatever this was. I'm going to go control divide for a fraction, and then 4,000, and then 1 plus 100. E, not the E on the alphabet. This E. That's a number. To the negative 0.5x. Make sure I typed it in right. Now I'm going to come back here. So that's F1. So F1 at 10. I need to round to a whole number because there are people. So it's 2,390. In part B, it says, how fast was the disease spreading on the 10th day? That's a rate. So I need to take the derivative and plug in 10. So how do I do that? Now that I defined it, this is going to be a lot easier. So I want to go menu calculus derivative at a point. So it's at the 10th day. And then it's just F1 at x, right? I already defined it. So it's spreading at 481 people per day. C. I know I'm going to have to flip the page over. Find the maximum point on the derivative. What does the x coordinate represent? What does the y coordinate represent? So to find the maximum of the derivative, you'd actually take the derivative of the derivative, the second derivative, and make it equal to 0 and solve it and know if it's a maximum. So I'm going to go menu, I'm going to go algebra, I'm going to solve. This is going to be the second derivative. See that one with the 2? Of f1 at x equal to 0, comma x. And I get only one answer, 9.210. This is B. So I took the second derivative equal to 0 because you use your calculator to show what you're doing. And then we get the answer 9.210. If I plug that into the y coordinate, which is the function, just go f1 at 9.210, and I get 2,000. So what does that x represent? So on day 9.210, which is just past the night, between 9 and 10 days, the disease was spreading the fastest. The rate was the highest. So the maximum rate, that means the disease was spreading the fastest at that time. And then when you plug in 2,000, that tells you how many people, right, at that moment had the disease. So it was 2,000 people. And the rate was the greatest. So the rate that people were getting the disease was the greatest. F. When was the rate of the disease increasing the fastest? And that would be the third derivative at 0. So the rate increasing. So the first question was, when was the maximum rate? And then when was the rate increasing the fastest? That's a rate of a rate of a rate. Ultimately, it's the third derivative equal to 0 to find the rate when it was increasing. So that's, first of all, the rate of a rate is a second derivative. And then you want to know a maximum. So then you take the derivative of that equal to 0 and solve it. So again, I'm going to go menu, I'm going to go algebra and solve. Here, see this one? This one I can put in any number. So I'm going to put in 3. That's the third derivative. f1 at x equals 0, comma x. And I get 6.576. So that was when the rate of the speed was increasing the fastest. Notice we have another answer, which is 11 point something. So we need to make sure we understand if that's a maximum or a minimum, that value. Believe it or not, let's see if this works. If I go here again, if I do the fourth derivative, oops. This is using the kind of like the second derivative test. So 6.576 is a maximum because it's concave down. That's ultimately what it's doing. So here's another way to test whether it's without a number line. So because the next derivative is negative, that makes that one a positive, or makes it a maximum. If I put in 11, I wonder what would happen if I put in 11.844. So at 11.884, that's a minimum because it's concave up because it's a positive answer. Anyways, a good one. So that's a maximum. So when was the rate of the speed increasing the fastest? So at day 6.5, right? The disease was spreading the fastest. All right. 18. A rancher plans to fence in 3 sides here, and he has 1,200 yards of fencing. What is the maximum area he can enclose? So the area is what I'm looking for. So the area of this rectangle is x times y. That's too many variables. You're also given fencing. The amount of fencing is 2x plus 1y, and that's equal to 1,200. That's the fencing. So y is equal to 1,200 minus 2x. Back here, plug in for y, 1,200 minus 2x. Distribute. Take the derivative. Equal to 0 and solve it. So I get 300. Make sure that's what you want. So if I plug in 1 into the derivative, I get a positive answer. If I plug in 400, I get a negative answer. So this is a maximum, and that's what I'm looking for. So what is the maximum area he can enclose? So I'm looking for area. So x is equal to 300. That means y is equal to 1,200 minus 2 times 300. So I'm using this, plug 300 for x. That's 600. So 1,200 take away 600 is 600. And then use the area formula. So x times y. And the maximum area is 18, 1, 2, 3, 4. So 180,000 feet squared, yards squared. That's the maximum area. Number 19. In number 19, you're given a function. Let's start there. So we're going to use the function and the first derivative only to graph this. So the denominator factors to x minus 2 squared. There's no hole in the graph. So the domain x can't equal 2. That creates a vertical asymptote. And it's even, so both ends go in the same direction. The end behavior, if I see the bottom is more powerful, so the end behavior is y equals 0, or you can write it as a limit as it approaches 0. The intercept, we have an x-intercept at -1. That comes from the numerator. If I plug 0 in for x, I get 1/4. That's the y-intercept. So that's all the good information I can get. There's no symmetry because the top has an odd exponent and the bottom has an even exponent. So the even odds are mixed together. So that's the pre-calculus work. So now if I wrote down the derivative, if I look at the numerator, we have a critical number at -4. That makes the top 0. If I plug in a -5, a negative times a negative is +5. take away 4, so it's a positive over a negative, which is negative. If I plug in negative 3, it's a negative over a negative, which is positive. So that's a minimum at negative 4. If I plug negative 4 into here to find the y coordinate, negative 4 plus 1, negative 4 take away 2, negative 6 squared, 36. So that's just a little bit below the axes. So there's a minimum at negative 4 and negative 1/12. Now I'm going to put all the information together that I have and draw my graph. So we have an asymptote at 2. Our end behavior is 0 on both ends. We have an x-intercept at negative 1, a y-intercept at a quarter, and we have a minimum point at negative 4, and it's just a little bit below. If I put this together, this is what it would look like. And I have my graph. Notice both sides are concave up. Number 20. It says find all the points of inflection. To find the points of inflection, I need to take the second derivative, but I first need the first derivative, then the second derivative, and then equal to 0. So these are odd at 0 and 4. So because these have odd exponents, the signs change at each one. So both of these are x values of points of inflection. So then you just have to plug that into the function to find the y coordinate, because they're asking for the points. So if you plug into the second derivative, a negative times a negative is positive, positive 1, and then 5 anyways. The signs change. So if I plug 0 in here, you get the answer negative 6. I'll help you with the other one. You plug 4 into here, kind of a headache, but you would get the answer negative 62. Number 21. Find all the extreme points. That's the turning points of y equals x over x cubed plus 4x. Step 1, I'm going to factor. I notice that there is something removable. We need to remove it first because that's not a turning point. So that's x squared plus 4. I need to take the first derivative. That's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. So I get negative 2x x squared plus 4 squared. So if I take the numerator equal to 0, I get 0. A negative and a negative, a positive number. So we have one extreme point at 0. But do you see what we removed? The domain restriction was that x can't equal 0. There's a hole at 0. So therefore, technically the hole creates a maximum, but there are no turning points. So our critical number is a hole, because that's what we removed. So therefore, there's no turning points there. Number 22. That's an end behavior question. The limit as x approaches infinity. That's power term over power term. So if I look at the power term on top and the power term on the bottom and I divide it, the end behavior is 1/5. 23. Find the C value for the mean value theorem. What's the mean value theorem? It's when I rock equals A rock. So from -2 to 0, it'd be f at 0 subtract f at -2 over 0 subtract -2. This is the function. You're going to plug in. So if I plug in 0, you get -5. If I plug in -2, you get 5. So that's -2 over -10 over 2, which is -5. The derivative is -9x squared minus 4x plus 3. I'm going to take the derivative and make it equal to -5. Add 5. So I have -9x squared minus 4x plus 3. To say you can use a calculator, you may use a calculator. So I'm going to use a calculator to solve that because it didn't look factorable. So menu, solve, algebra solve. And we're going to type that in. -9x squared plus minus 4x plus 8 equals 0, comma x. Be careful. It goes from the -2 to 0. So, therefore, 0.746, cross it out. It's not in the interval, so the only answer is -1.191. (24). You need to write this down, but I'm going to do it right in my book. In 25, you're given the velocity equation. Find the object's acceleration at 5. Acceleration is the derivative of velocity, so we're looking for slope. So at 5, the slope is down 3 and to the right 2. Is that right? Down, sorry, how many is it down? Down 3, down 6 to the right thing, or I could just do it right there, right? So down 3 and to the right 1. So it's -3. And how would you write that properly? Would be feet per second squared. Find the speed of the object at 6 seconds. Speed is the absolute value of velocity. So at 6 seconds, the velocity is -3, so the absolute value of that would be +3 feet per second. On which interval of time is the object moving to the right? So it's moving to the right when it's above, right? So from 0 to 5, it's moving to the right. At 0, it's above, but at 5, it's at 0. So one is closed and the other one is open, just so you know. On which interval of time is the object's velocity increasing? So velocity would be increasing when the slope is rising. So from 0 to 2, it's increasing. And from 6 to 7. 28, on which interval time is the object's speed increasing? Speed increases when acceleration and velocity have the same sign. So what we're looking for is increasing and above. So increasing and above, that's 0 to 2. or we're looking for decreasing and below. So if it's decreasing and below, the signs match. That's 5 to 6. So from 0 to 2, it's increasing and above, decreasing and below, the signs match. That's when speed is increasing. At what time is the object farthest to the right? So it's going to start here and it keeps going to the right, then to the left. So obviously right here at 5, it's the furthest to the right. After 5, it changes direction and goes back the other way. While I'm here in the book, I might as well just do it. I have room. Again, you need to write it down in your math notebook, but I'm going to do it here. A rectangle's position, this is y equals cosine x. Find the point so that the area of this rectangle is a maximum. So this rectangle is 2 x's and a y. So the area would be x times y, or 2x times y. I think of it as x times y and you double it. Or 2x times y, that's also the area. You're told that y equals cosine x, so to have one variable, you'd plug that in for y, take the derivative. This can be the product rule. The first times the derivative of the second, plus the second times the derivative of the first, make it equal to 0, and you're going to solve it. Oh, to solve the equation. Well, that's nice of us. So let's use this to solve an equation. And if this is cosine x, right here is pi over 2. That's when cosine is 0. So from 0 to pi over 2. So I'm looking from 0 to pi over 2. So let's type this in. So I'm going to go menu, algebra, and solve. The equation is 2x times negative sine x plus, I'm going to put 2 first, so plus 2 times cosine x. You could have went times 2 afterwards, and that's when it's equal to 0, comma x. Now I'm going to put a domain restriction down, so I hope this works. So I'm going to go control equals, and I'm going to put a line here, and then I'm going to put the restriction down, which is 0 to pi over 2. See, a trig equation is cyclical. There's an infinite number of answers because it keeps going up and down, up and down. So I need to put a domain restriction down to get an actual answer in my restriction. Oops, why did I have I? It's not what I wanted. I just wanted pi over 2. All right, you ready? Let's hope this works. So I get 0.860. That is the right answer. So to have the skill to put a domain restriction in for a trig equation is a good big skill to have. 0.860. How would I know? Remember the little trick I did before? How would I know if that's a maximum or a minimum? Is I would take the second derivative. So if I think, here, let me do it this way. So if I take the second derivative, and I'm taking the second derivative of 2x times cosine x. So if I take the second derivative of that and I evaluate it at that critical number, 0.860, if it's positive, it's a minimum. If it's negative, it's a maximum. So a negative means that's a maximum answer because it's concave down. So that's good. Oops, let me put it in here. So this is what I found out. it's 0.860. When I did the second derivative at 0.860, that answer is greater than 0, which means that is a maximum. That's what we found out. And then it says find the what? The point. So I also need the y coordinate. So then I need to plug in 0.860 in for cosine. Here. So use your calculator, cosine 0.860. And I get 0.652. So at 0.860 and 0.652, at that point, the rectangle has a maximum area. Beautiful. All right. Mr. G Math over and out. I'm proud of you for doing your work, not giving up even when it's hard. Until next time.